All right, so a couple of things on that homework that I handed back. Let's see. So here's an example of what homework ought to be. Well, that's not the, that's a little small, isn't it? Let's see, slideshow. Where did they put that now? Insert design, transition, slideshow. Current slide, yeah, which one? There we go. It's just, escape. Oh, goodness. That big as we can. And then we'll go back in the slideshow. We'll try that again. Okay, there we go. So that's basically what the homework ought to look like. Okay, so we got name, date, problem number, page number, got an abbreviated problem statement there. We got a sketch that shows what's going on on the right there. Work through the problem, and then I've got that kind of covered up, but I've got all the answers in one box. Okay, so that's how I'd like things to be. It just makes it easier for me to go through the 40 some of these that I've got and grade them efficiently. Okay, so that's the format that we're looking for on that. All right, and you know, starting next week, I'll kind of grade a little bit on format. So just understand that your stuff, you know, ought to be fairly neat and legible and done something like that. All right. And as I said, that's kind of what they expect when you're working in this industry. And it just looks a little bit more professional and that sort of thing, which is what you want to develop. All right. Also, I think more organized work leads to less mistakes too, which is good. All right, so if you have some notes on there, SE means use a straight edge. One box means put all the answers to a problem in one box. It just makes it easier for me to find stuff and grade it. If they're scattered around in different boxes, I got to hunt around more and burns up a little bit more time. Okay, PS means include a problem statement. You want someone else to be able to look over what you're doing and understand what you're up to. That's why you put a problem statement on there. So it's nice and clear what you're trying to accomplish. Can't read means I can't read your writing. I don't care if it's neat or not really, but the real test is can somebody else read it? And if they can't, it's a problem. I mean, if you're writing stuff down and people can't read it, that's a problem. So that's just some of the notes you might see on your homework, okay? And like I say, don't spend 5 hours carefully crafting your homework. Just work on it a little bit every time. Slow down just a bit and work on it and get better at it. It'll pay off when you start working and all that, I think. Okay. All right. So that's that. Any questions on that stuff? Okay. All right. Well, we keep kind of going on with this stuff, so we've got some things that are coming due, tomorrow, right? Is it? Okay, so what do we have coming due tomorrow? Is it these position vector ones? It is, isn't it? And then is it the dot product too? Yeah. Okay, great, thanks. All right, so here's 151. I don't know if we've got questions on that, but what you're doing with that one is you're just adding the two vectors together. They're given based on positions, so you have to find the position vectors and then go through that process to turn them into force vectors. So step one is to find the coordinates. So, you should be able to read those dimensions. That's one thing I'd like you to be able to do. Right. So if a dashed line is parallel to a given axis, it's a dimension in the direction of the axis. So for instance, here we got 4, that's going in the negative x. There's 3 in the z, positive, and 5 in the y, positive. So that's -4, 5, 3 for B. just as an example. All right. So that's one skill you want to have, in this class, is being able to do that. If we're going to work on AB, remember to find RAB. Now R designates a position vector. What you're going to do, you're going to take B minus A. So as we just went over there, B is negative 4, 5, 3. When you work out A, that's 1, 6, 2. So subtract A from B. You'll get negative 5, 1, 1. That's the position vector from A to B. Essentially, that's a set of instructions to start at A and go to B. So you go back in the X5, you go negative Y1, and you go down in the Z1. Okay, then you find the length of that vector by taking the square root of the sum of the squares. Okay. So you take the square of each of the three components of RAB, add them up, and take a square root, and it comes out to be 5.2. All right. So that's the length of the line from A to B. Now that's not something you want in your force vector. You want to get that out of the force vector. Okay. How long that line is doesn't really matter. You want to take that position vector from A to B and turn it into a unit position vector of length 1. Okay. So what you do is you divide the whole vector by 5.2.
The vector, shouldn't one of those be positive? The ones? 3 minus 2.
Yeah, I busted that, didn't I? Yeah, it's my bad. So, yeah, I've got a couple little signers. So let's correct them in red so you can see what I'm doing here. Yeah, I've got some busts here. This ought to be positive 1 here. So we'll change that to positive. That ought to be negative there as well. Okay, so that one to the left is negative, but that one, yeah, 3 minus 2 should be positive. Looks like I just switched them down here. That should be positive. This one should be negative. And actually, it should be plus negative 1 squared. As I've mentioned, the actual putting the signs in the square root calculation really doesn't make any difference, but I do like to put them in there so I don't drop them later, just to be kind of systematic. So yeah, I've got a couple little busts on that. So that should be minus 5, minus 1, positive 1 is what it ought to be. The square root's the same, though. It's 5.2. Doesn't make any difference there. Okay. So we good with that? We got any questions? Okay. Good. All right. So then we divide through by 5.2. So to find that unit vector, I take 5 minus 1 positive 1. So it looks like it's correct here in this middle column there. Divide each term by 5.2. So I get negative 0.692, negative 0.192, and positive 0.192. Okay. So that's a unit vector. That has a length of 1. That's its magnitude. Plus, it points the direction from A to B. It tells how to direct yourself to get from A to B. Okay. So now I've got the unit vector. To turn that into a force vector, I'll scale it up by 210. Okay. So what I do there on the right-hand column, I just take that unit vector, which has a magnitude of 1, and I scale it up by 210. So I multiply each term by 210. So what I'm doing there, I'm taking a unit vector of magnitude 1 and scaling it up by 210. So the magnitude of that vector then will be 210. Okay? 1 times 210 gets you 210. And then I just factor that through each of the components. So 210 times 0.962 times negative 0.192 and times positive 0.192. And that gets me the force vector. It has a magnitude of 210, and the proportions of x, y, and z are proper to point it from A to B. I mean, that's basically what's happening there. Okay, so that's the force vector. So that's the process for doing that. Okay. Any questions on that? All right, so that's how you do that. And, you know, it's something you should know. Okay, for sure, you should know how to do that kind of step by step. All right, now what you would do, you do the same thing for AC. Okay, so same process for AC. And then once you've got that, you'll just add the components together. So you got negative 202, negative 40.4, and positive 40.4. So you're going to have negative 202, 40.4, and 40.4, and that's FAB. Okay. And I think the negative was here, wasn't it? Yeah, okay. And then what you'll do, you'll also get FAC. And that's going to have three components as well. You know, these are Cartesian vectors at x, y, and z. So that'll be FACX, FACY, and FACZ is what that'll be. Okay. And then what you do with that is you just add them up. So you just add up the x's, add up the y's, add up the z's, and what that'll get you then is the resultant, FR. Okay. So you'll get those three values figured out. They're just sums. And then once you've got them, you got the resultant vector. Okay. Got any questions on that? Doing all right? So that's the process on doing these position vector to force vectors. Okay. Now 153 is maybe a little bit trickier. Do we got any questions on 153? I'll go over it a bit, but do we got any questions on that one? All right, now 153, what's going on there? You've got point C, and that, you can find the coordinate of point C pretty readily. Just work your way up the z-axis, and you can get the z coordinate on that, easy enough. Now, coordinate B is sometimes a little tricky. So what you would do with that is you would use that 32-degree angle that's given. And that, think of AB as being part of a door that's hinged on the x-axis. And what's happening to that thing is it's just rotating about the hinges, okay? So if this is on the x-axis here, it just kind of, it starts off being in the, think of it as starting in the xy plane, and then it just rotates down 32 degrees, okay? That's what's going on. So what you're doing is you're looking down the x-axis. So that point A that's shown there in my sketch in red, that's basically the x-axis, okay? And then that door rotates down from that. It has a length of 2.10 meters. So that is the hypotenuse of a right triangle, okay? So what you're going to have there is you're going to have the y and z coordinates there are just based on the legs of the triangle. I mean, that's basically it, okay? So you just have to do a little bit more work to find the coordinate of B. You know, you've got X given right there. And then Y and Z will come from that triangle. So it's just a matter of doing some right triangle trig on that thing is really about it, okay? So for instance, if you do cosine 32 times 2.10, you get 1.78. That's one of the legs of that triangle. You need to find the other for the Z coordinate. So the coordinate of B is 4.3 in the X. Cosine 32 times 2.1, which is 1.78 in the Y, and then you'd have to find the Z. Okay? Once you do that, you'll have the coordinate of point B, and then you've got it for C. So then after you got that, you just do the stuff that we went over there a minute ago, that process where you've got the coordinate of C, the coordinate of B, and you just go through the whole business there. Take C minus B to get a position vector from B to C, find its magnitude, which is the length of the line, divide through by that to get a unit vector, and then scale it up by whatever that force magnitude is, which I can't remember at the moment. It's 900 newtons. So you do the same sort of thing that you've done, like that. So there's just some of the intermediate answers if you want them to kind of check. On this 3D stuff, it's good to have those. So RBC from B to C is negative 4.3, 1.78, negative, and 5.01. The length of that is 6.84, and then the unit vector from B to C is negative 0.629 and negative 0.260 and 0.733. And then the force vector is just taking that unit vector and scaling it up by, 900, I think it is?
Yeah.
Okay, so that's negative 566 and negative 234 and 660. So just some checks there as you go through it. So we okay with that? Just that extra little bit of working through that right triangle to get to the original coordinate of B is the process on that. All right, so that's the position vector type problem. So again, any questions on those? We're doing all right? Okay. All right, then we got the cross product deal, or the dot product deals, okay? So there's 162. All right, so this is another process that you should know. Why don't we look in detail at 163. So what we want to do is find the tension and shear in that strut BC. Okay. So to do this, this is 163 is what this is. First thing you want to do is you want to, of course, get the coordinates of the points, which are showed by those dimensions. Okay, once you've done that, you just want to go through the steps and find the force that goes from B to A. So take RA minus RB and get the position vector from B to A, 4 minus 6, 5. Find the magnitude, 8.775, and divide through that to get the unit vector, 0.456, negative 0.684, and 0.570. Then scale that up by 800. So if you do all that stuff, you'll get the vector, the force vector, from B to A, 365 minus 547 and 456. Okay, so that's the force vector that starts at B and goes to A. So you got any questions on that bit? Yeah, question?
If we did it force AB rather than BA, because I noticed the first time I did this through with BA, I got a negative tension number. Does it matter which way we show it?
Okay, so the question is, could you, I've got force BA here. Could you use force AB? And the reason that was done is because you got a negative answer when you work through it for your component, for your tension. The answer to that is no. You can't switch forces like you do position vectors on dot products. And the reason is this force is distinct. It does go from B to A. By the direction of that arrow, you want to get FBA. Now, my thinking as to why you got a negative answer for your tension is you probably used a position vector from B to C, be my guess.
B to C?
Yeah, when you did that. And this is my guess. I'm just guessing as to why you got a negative tension. You probably want the position vector going from B to C.
Yeah, I guess just kind of in line with the other problems, I noticed that, I originally did it BA just as you've done there, and then I switched it to FAB because I was getting a negative tension value.
Yeah, and my guess is you were getting a negative tension value because it's not due to the force vector. The force vector has to be from B to A because that's how the arrow points.
Okay.
You do have options on which position vector to use.
Okay.
And my guess is you used a position vector from B to C.
All right.
And that's why you got a negative answer.
So on a test, if we did FAB, it would be wrong.
Yeah, I'd take something off for that because it isn't going from A to B, it's going from B to A. Now, if you got a negative vector for your tension, I wouldn't take anything off for that as long as you realized it was tension and wrote it down as such.
Okay.
See, my guess is your position vector went like I have in green there from B to C.
Well, if you alternate either, you'll end up getting the positive tension.
Correct.
So, like for this, you just have to switch the U to CB rather than UBC.
Yes, correct. Right. But it's technically not correct to call that FAB because it's not. It's going from B to A. The position vector, you can really say it's going either way. There really isn't a definite specification on that.
All right.
Now, see what's going on. If you went with from B to C, you're assuming the projection of force goes from B to C, which is really compression. That's taking B and pushing it towards C.
Yeah.
What's happening to B is it's going that way. That's tension.
I was more likely to switch the force though because it said in the problem cable AB. So I was thinking that maybe to do force AB was incorrect initially.
Or BA, I think you meant there. It is BA. Yeah, it's BA because it's pulling. And that's what it's doing. So the option is to switch to position vector, not the force vector.
Okay.
And the reason I want to go from C to B is that's the direction it pulls. That's the component. That's which way it actually goes, the component in the strut there. is not from B to C into the page, it's from C to the B coming kind of out of the page, so to speak. And that's why, you're right. If you switch either one, you'll get mathematically the right answer.
Right.
But theoretically, it's correct to switch the position vector, not the force vector.
Okay.
Okay. Other questions on that bit? Okay, so that's FBA. Okay. Now the next thing is to go through the stuff where you find a unit vector for that strut, or whatever you want to call it, the structural member, whatever you want to call the thing. And so you just find a position vector, and I did it from C to B. I kind of was looking ahead on that, and I said, okay, that tension is going to pull on B. It's going to go that direction. So that's why I used UCB. So I took RB minus RC, found its magnitude, divided through, and got a unit vector. Okay. Now when I use this unit vector, I'll get a positive answer. Now again, if you got a negative answer, you could have just flipped the sign, just left it at that. It would have been fine. It's not like you have to.
I have to redo everything and switch both of what I did, because I initially just switched the force and I had it right the first time.
Right. Well, just change the signs on it, and then change the signs. It's not a huge, it's not a big deal. When that happened, you just could have just flipped the sign immediately. You don't have to recalculate anything or anything like that.
Yeah.
All it means is the position vector is going the opposite direction. It's no big deal. Okay. All right, so there's the unit vector in the strut, 0.707, negative 0.566, and negative 0.424. All right. Okay, so then you just take the force vector and you dot it with the unit position vector, and that gets you, in this case, the tension. Okay. So you're just going to do a dot product between the two. All a dot product is you multiply the like components together and add up those three products. That's how you do a dot product. Okay. Okay, so the tension is F dotted with U, so I just take the like components, multiply them together, and add up the three products. So I get 278 plus 309 minus 193, that's 374 newtons. So if you pull on that strut with a cable with 800 newtons in the position shown, you'll get a tension in the strut of 374 newtons. Okay. So that'll be 374 newtons. Now the rest of that cable force will go into a shear, which does something like that, okay? So there's a right angle there. Okay, so that's what's going on. That force, we're basically resolving it into two components. One along the line of the strut, and the other normal to that. Okay. So this is 707. When you do the theorem of Pythagoras, you can get to this component right there, 707. Okay, right there. What I'm doing there, I'm taking the total, the hypotenuse squared, minus the one component I found squared, and then I'm taking a square root. Okay. So we okay with finding, doing the dot products and finding the shear? Now, I think this problem just asks for the magnitude of the shear, so that's the quick way to get it, right there. Just do Thermic Pythagoras. Remember, you're subtracting in this case, because you have the total, you have the hypotenuse. You want to find one of the legs, one of the components. So you 800 squared minus 374 squared. That's what you want, all right? Okay. Now, if you want to do it the long way, which you'll have to do on the previous problem, because I asked for a vector, so it might be good to be sure you understand this. If you're going to use vectors, and this is how you'll have to do it on the previous problem, on whatever 162 or whatever that is, you're going to first find the tension as a vector, okay? So you're going to take the magnitude of the tension times the unit vector from C to B. And that's going to get you a tension vector, like so. And then once you've got that, you'll take the total vector, the original 800 Newton vector, from B to A, and that's 365 minus 547, 456. And then subtract off the tension vector, okay? So you're going to subtract each component out, like so, and you're going to get 101 minus 335, 615 for the shear vector. So this vector going up this way is 101, negative 335, and 615. This vector going this way here is 264, negative 212, negative 159. Okay. So you're finding each vector in this case. And that's all based on knowing that original hypotenuse, which is the 800 Newton vector, which we found. And that's 365 minus 547 and 456. Okay? So that's what we're up to there. So this is the vector approach to finding the shear. Take the total and subtract off the one you know, which is the tension, and then you can find the one you don't, which is the shear. And then if you want to know its magnitude, you take the square root of some of the squares, 707.
Is that just because it has for the magnitude and the vector?
That one on 263, yeah, I think I just asked for the magnitude, but on it's 163, but on 162 I asked for both, so I'm kind of modeling how to do it for you, right? So 162, right, it's because I asked for both magnitude and vector. That's why I'm showing you this. Yeah.
But on a test, if it just asks for the magnitude, we could do it Pythagoras.
Right, if it's just a magnitude, just do the Pythagorean theorem, you're done. But if it's a vector, you'd have to go through this process. Okay. So are there any questions on this one, 163, or particularly 162, that apply to that one? Now, the one thing I'd point out about these is these 3D problems are like, they're like processes, you know? Do this, do that, do that, do that. When you study this stuff, just figure out what the steps are. You know, if I gotta find a force vector from position vectors, you know, how do I do that? What are the steps? If I gotta do a dot product, what are the steps? You know, just kind of think about it in that fashion. It's not like these 3D things, they're often not like problems where they're real, I don't know, tricky, you know, you're not scratching your head saying, well, what do I have to do? It's more, how do I do it? And it's very regimented in how you do this stuff. Bang, bang, bang. So just kind of look at it in that fashion when you're studying it and all that. Okay. All right, so that's what's due tomorrow. We're about out of time here. I think we'll probably call it good if there are any questions. Okay.
I'll shoot you an email and just remind you. Oh, sorry.
Basically, take every number, reverse, erase, switch.
Let's see how we go.
I